The Land Rehabilitation Guidelines for Surface Coal Mines was undertaken by the Land Rehabilitation Society of Southern Africa, funded by Coaltech Research Association and supported by the Minerals Council of South Africa. We encourage you to familiarize yourself with the full document available from larsa.co.za or coaltech.co.za. Mining is the 5th largest industry in the world. It has a significant role to play in underpinning the prosperity of current and future generations. South Africa is home to 3.5% of the world's coal resources and is ranked as the 6th largest coal exporting nation. In this video and the guideline document, we focus on surface coal mining, both open pit and strip mining. Mining-related rehabilitation should be undertaken progressively. It should start from the time of construction. We differentiate between the following stages of the rehabilitation process: topsoil stripping, subsoil stripping, mining or dragline, spose leveling, subsoil placement and leveling, topsoil placement and leveling, and fertilizing and seeding of soiled areas. This framework could be used to compile a site-specific rehabilitation plan for a surface coal mine. These steps are undertaken as a continual cyclical process. Focused and well-managed on-site implementation of the rehabilitation action is critical for a successful rehabilitation outcome. This section provides guidance for the following core components of land rehabilitation: surface landform design and profiling, soil stripping, stockpiling and replacement, soil amelioration, revegetation, and surface infrastructure. Landform recreation actions are to develop a post-mining surface landform design at the planning stage. Include landform designs for the rehabilitated box-cut spoils, final voids, and overburden dumps if these remain at closure. Comply with land capability commitments. Reduce slope length on large overburden mounds or in rehabilitated areas with excessive slope length by increasing drainage density. Manage the effects of surface settlement on the reprofiled landscape. Manage subsurface drainage, groundwater flow. Monitor spoil reshaping to ensure conformance to the requirements of the model landform design. Assess the effects of changes to mine plan on final landform. For soil stripping, actions include: ensure that there is a detailed soil survey for the areas to be stripped. Generate a soil stripping and handling plan. A georeference survey defining soil types with horizons and depths to be stripped. Areas to be stripped and when stripping should be done, plus volumes of different types of soil available for rehabilitation. Where the various strip soil horizons are to be placed. The proposed final distribution of replaced soils, the types of soil material used and thickness applied. Strip a suitable distance ahead of mining to avoid soil loss and contamination from throw or blast rock. As a norm, soil stripping should be kept within 3 to 9 months of mining, or at least 100 meters ahead of the active mining phase. Demarcate boundaries of different soil types. Define usable soils cut-off horizons in simple terms that the stripping operator can understand. Supervise stripping to ensure that different soils, for example well-drained soils versus clayey wetland soils, are not mixed. Strip soils only when moisture content will minimize compaction risk. Soils must be below their plasticity limit when handled. Strip and replace soils in one process wherever possible. Use a shovel and truck feet instead of bowl scrapers. Preventing soil compaction during soil handling should be a priority focus for all rehabilitation activities. For soil stockpiling, actions include: locate and manage soil stockpiles so that rehandling is minimized. Ensure stockpiles are located outside of drainage lines and placed in free draining areas so as to minimize waterlogging and soil erosion losses. Minimize compaction during stockpile construction. The use of heavy equipment over soil piles damages the soil structure. Design stockpiles to maintain a maximum level of biological activity. Revegetate to condition the soil and avoid erosion losses. If soil stockpiles were created by loose tipping, piles should be planted and fertilized by hand. For soil replacement, actions include: replace different soil types in their correct slope positions. Red and yellow-brown soils belong on the crest and upslope areas, while grey soils with hydromorphic characteristics belong on the lower slopes, and dark hydromorphic clays belong in the bottomlands. Retain a soil reserve to repair localized surface subsidence areas and soil cover losses. Minimize compaction of replaced soils during replacement. For soil amelioration, actions include: following soil placement, apply lime and superphosphate fertilizer as required, and rub all soils to the full depth of the replaced soil layer. Apply and incorporate, by disking, any additional chemical ameliorants required to condition the soil for optimal plant growth. Till the soils to produce a seedbed suitable for the plant species selected for seeding. Top dress soils with appropriate fertilizer to supply the required levels of nitrogen, potassium, and phosphorus, as determined by soil analysis. For revegetation, actions include: identify species well adapted to local climatic conditions and that can provide functional use as part of the predefined post-mining land use. Plan to sow or plant when seasonal conditions are most likely to ensure successful germination and growth. Apply planting methods best suited for the surface landform profile and species selected. Apply appropriate sowing and planting rates. Apply ongoing maintenance on establishing vegetation. Once established, vegetation still requires regular maintenance. When the growth medium comprises low fertility soils or overburden, vegetation maintenance requires regular application of plant nutrients, either in the form of inorganic fertilizers or manure, until the natural fertility cycle has been restored. Normally, fertilization continues annually for at least 3 years, and subsequently only every 3 years, as required and informed by soil analysis. Control invasive alien species. The most effective is to prevent the invasion in the first place. A weed management plan is necessary to prioritize actions and resources. Implement biodiversity offsets as a last resort, only if on-site rehabilitation is not possible. Surface infrastructure. Actions include: compile a surface infrastructure assets register that clearly describes surface infrastructure items that 1. May have beneficial reuse potential for future land users, 2. Need to be decommissioned, demolished, and removed, or 3. Have salvage value on-site or off-site. Prior to reuse, removal, or demolition, All hazardous and coal-contaminated materials and areas must be made safe. Ensure that any infrastructure remaining as part of the rehabilitated landscape is safe and stable, according to professionally engineered designs. Remove structures identified for off-site reuse, recycling, or demolition. Safety is an imperative, particularly where tall structures are concerned. Compile formal agreements for handover and long-term management of remaining infrastructure. Successful rehabilitation depends on 1. The technical quality and quantity of the environmental data collected at a site, and 2. On the site's ability to react to the knowledge gained from that data. Effective monitoring and evaluation of the progress of the physical aspects of rehabilitation are critical during the operational phase as well as during the re-establishment of the desired final land use functions and services. Key objectives of rehabilitation monitoring are to verify that rehabilitation actions are being done according to plan, on time, with the expected results. Ensure enough time for corrective action where rehabilitation actions have not resulted in the desired outcome, and verify that the relinquishment criteria have been met so that the mine can apply for closure. Some general principles of rehabilitation monitoring are: initiate monitoring before the start of rehabilitation operations. This will establish the baseline values from which to track rehabilitation. Track the progress of physical site attributes and biological attributes. Use monitoring data on physical attributes to calibrate outputs of risk-based prediction models. For landform profiling, we look at the alignment of actual final topography to agreed plan landform, erosion, surface water drainage systems and surface water quality, and groundwater quality at agreed locations. Predictive modeling is often the preferred means of quantifying the outcomes of rehabilitation projects and defining monitoring criteria. It is also useful for comparing different scenarios for rehabilitation. For any land to have production potential, irrespective of the land use, the soil and the plant cover will need ongoing care and maintenance. Rehabilitated coal mined land might need even more focus than land unaffected by previous mining activities. The site's transfer agreements to any post-mining landowner must allow for this ongoing land management. Conducting a site-wide climate change model is useful in identifying rehabilitation aspects that are most at risk. Mine rehabilitation should aim to meet environmental management plan commitments for post-mining land capability, or to meet revised rehabilitation targets agreed with all stakeholders during the operational phase. Let's look at the ongoing land management as part of the entire mining life cycle and beyond. The objectives of post-mining land management planning are to ensure optimal long-term management of the rehabilitated landscape, manage the rehabilitated mining landscape's residual and potential latent liabilities, and limit the mine's long-term financial responsibility for rehabilitated areas. Successful rehabilitation is the state in which rehabilitated land is sustainable in the long term and can support viable agriculture or other enterprises. A residual risk is, for example, the presence of invasive species seed in quantities that are viable to cause future infestation. The risk is understood and can be managed. On the other hand, a latent risk is, for example, the possibility that sometime in the future, water from the rehabilitated land may become acidic. It is not certain that the waters will turn acidic. They could, depending on the relative rates of generation of acid from oxidation of sulfides and the neutralization from the release of carbonates. A post-mining land management plan should be compiled as the site nears application for a closure certificate. Thank you for your time. Successful mineland rehabilitation is our responsibility. Remember to visit larsa.co.za or coltech.co.za for the full guideline document.